So this problem asks us to maximize the function p. So maximize p is equal to 2x plus y, subject to the constraints given by the 4 inequalities. So the first thing we can talk about are the bottom 2 inequalities. The x is greater than or equal to 0, and the y is greater than or equal to 0. So both of those constraints lead us to the quadrant 1, the first quadrant. So it's a quadrant where all x's are positive and all y's are positive, or they can be 0, so we can say non-negative. So in this quadrant 1, so I focused on the quadrant 1, and that quadrant takes care of the x is greater than or equal to 0 and the y is greater than or equal to 0. So in other words, normally you see something that looks like this, where you have the x-axis and the y-axis, and the x is greater than or equal to 0 would lead you to say, okay, that has to be everything above the x-axis, and the y is greater than or equal to 0 leads to you to believe that it has to be to the right of the y-axis. And so you can see that the only section we're interested in is this part right here. Again, that's quadrant 1. So I have just focused on quadrant 1. So the way my graph is set up, it's going to already kind of be taking those last 2 constraints into account. So those 2 are taken care of with the way it's set up. So now what I need to look at is the additional information given by the first 2 inequalities. When I am graphing inequalities, I really like to isolate my y on the left and then go from there. And so that's what I'm going to do in these cases. So for the top one, this 18x plus 5y is less than or equal to 90. I'm going to go ahead and solve that for y. And there's more than one way to do this. So if you have another way that works for you, please go ahead and do that. But this is just what works for me. So I'm going to subtract the 18x from both sides, and that will give me 5y is less than or equal to negative 18x plus 90. And then to finish isolating the y, I'm going to divide by 5. And so that will give me y is less than or equal to negative 18 over 5x plus 90 divided by 5 is 18. All right, so there's one inequality, the first one, solved for y. Okay, so now I can go ahead and graph that one. So 18 is our y-intercept, and then our slope is negative 18 over 5, so I'm going to go down 18 over 5. So right there. And then we can just connect those in a solid line because it's or equal to. Okay. And then since its y is less than that, that will be in this direction. So less than will be below that line. And now I'm going to do the same thing with the second inequality. So for the second inequality, I'm going to do the same thing. So I'm going to solve for y. So 12x plus 10y is less than or equal to 120. So subtract 12x from both sides. So we would get 10y is less than or equal to negative 12x plus 120. Divide by 10. And so y is less than or equal to negative, let's see, that's going to be 6 over 5x plus 12. So I have now isolated the y for this one. So my second inequality is y is less than or equal to negative 6/5 x plus 12. So to graph this one, I can see that my y-intercept is 12, And then my slope is negative 6/5. So I would go down 6, right 5. And then down 6, right 5. And connect those. Since it's or equal to, it will be a solid line. Okay. And since it's a less than, it will be everything below that blue line. So the part that is included in our feasibility region is everything below the blue line and below the red line and above the x-axis and to the right of the y-axis. So that is going to be this region that I'm going to color in right here. So that is called the feasibility region. The feasibility region. And the feasibility region is the region of values that are feasible to satisfy all of the conditions given in the system of inequalities. So let me erase this over here. So once you graph all of your inequalities that you're given and you see the part where it meets all the criteria, again, that's called your feasibility region. In order to maximize or minimize, depending on what you're asked to do, in this example we were asked to maximize, you look at the corners. So if you look at all the corners, here's one, here's one, here's one, and here's one. So you're looking at all the places where two parts, two lines intersect. Those are your corners. One of the corners is going to maximize your function, whatever it is. In our case, we're looking at this function. So one of the ordered pairs at the corners is going to maximize that, and one of the corners is going to minimize that. So your optimization, whether that's maximizing or minimizing, will occur at one of these corners. If it's completely bounded like this. It's a little bit different if you have an unbounded region. But for this bounded region, we can maximize and minimize the function given. So our next goal is to find out where all of those points are. And so I've kind of blacked those in, but let me undo. This point right here, it looks like it could be at 3, 8. Okay, but that's a guess. Remember that this is hand drawn, and so that could actually be a little bit to the right of 3, or, it might not be exactly at that ordered pair. So we have to really be careful with that. We do know the intercepts, and we do know 0, 0. So those are definitely clear. So 0, 0 is one option. That could be an ordered pair that may maximize or may minimize our function. We know that 0, 12 is also an option. And if you weren't sure, what you could do is this. This point right here that I'm saying is 0, 12, notice it's associated with the blue line. So the blue line, we have 12x plus 10y is less than or equal to 120. That is the blue line's y-intercept. So if I wanted to know for sure that that was 0, 12, I could find the blue line's intercept. Find the y-intercept, because I want to see where that blue crosses the y-axis. And you would do that by letting x equal 0. And so you would have 12 times 0 plus 10y is equal to 120. Divide by 10, so y is equal to 12. So right there I see that yes, that point is indeed 0, 12. And I could do the same thing for the x-intercept. So notice the x-intercept is associated with the red line. So I would need to find the x-intercept of the red line to verify the point. I think it's probably 5, 0, but again, you really want to verify and make sure. So 18x plus 5y is equal to 90. I'm going to find the x-intercept. That means let y equal 0. So that will be 18x plus 5 times 0 is equal to 90. So 18x is equal to 90. Divide by 18. 90 divided by 18 is 5. And that's what I thought, right? So that's 5, 0. Okay, so now I just have this last point here. I think it's 3, 8, but I want to check. Notice that that point is the intersection of the red and the blue lines. So that is where those two lines intersect. And if you remember from a previous lesson, you can find the intersection point by solving the system of equations. So we're going to write the associated equations for the red and the blue if they were just lines. So 18x plus 5y is equal to 90, and the blue is 12x plus 10y is equal to 120. And so to find this point, and maybe we should label the points. Let's say this is A, B, C, and D. So to find point B, we want to solve the system of equations. So we're going to solve the system of equations because that tells us what that point is, where these two lines intersect. So to do that, remember we had the elimination method, and if you don't remember this, go back and rewatch a video about how to solve a system of equations. We want to eliminate one of the variables, and I'm going to look at the y. So if I multiply the top equation by a -2, that will give me a -10y, which will cancel out with the 10y in the equation below. So this is going to give me a -36x minus 10y is equal to a -180. In the second equation, I'm not changing. And you'll see that when I add these equations together, the y values cancel. I have -10y and a +10y. So since those are opposites, they cross out, and then I'm going to combine the rest of it. So -36x plus 12x is -24x. -180 plus 120 is -60. And divide by -24. So 60 divided by 24, it doesn't go in evenly, but they are both divisible by 6, so we can try that. So negative divided by negative is going to be a positive. If I divide by a 6, I'm going to get 10 over 4. And I can see that now I can divide by 2. So that's going to go to 5 halves. And that's the lowest terms. Notice that my x value is not 3. My x value is 5 halves, or 2.5, or 2.5. So my guess of 3, 8 was not correct. So if I just assumed that I drew a perfect graph and I used 3, 8, I would be wrong. Okay, so that's why you really need to make sure you check mathematically. So point B has an x value of 2.5. And now I need to find the y value. So remember, to find the y value, you take the x value that you just found and plug it into one of the equations and then solve for y. So 5 halves, I'm just going to plug it into the top equation. So 18 times x, so 18 times 5 halves, plus 5y is equal to 90. So 18 times 5 is 90, divided by 2 is 45. So that will be 45 plus 5y is equal to 90. I subtract 45 from both sides, so I get 5y is equal to 45. I divide by 5, and I see y is equal to 9. So now I see my y value is 9. In my graph, it doesn't even look like 9. It looks like 8. But mathematically, I've shown that it's 9. So my ordered pair for point B is 2.5, 9. Okay, so now that I have found all my points, what I want to do is see which of the points maximizes the function that I was asked to maximize. So I was asked to maximize p is equal to 2x plus y. So let's put all of our points down. We have point A is 0, 12. Point B is 2.5, 9. Point C is 5, 0. And point D is 0, 0. So these 4 points give us our possibilities for maximizing the function p is equal to 2x plus y. So now our goal is to just plug these in for x and y and see which one gives us the largest number. So for A, kind of make a little chart here. For A, we have 2x. So remember our function is 2x plus y. So 2x, x is 0, plus y is 12. So that's going to be 0 plus 12, which is 12. Okay, now I'm going to do the same with 2.5, 9. So 2 times 2.5 plus 9. So 2 times 2.5 is 5. So that's going to be 5 plus 9, which is 14. Okay, next point, we have 2 times x, which is 5, plus y, which is 0. So that's just going to be 10 plus 0, which is 10. And then lastly, I have 0, 0. So 2 times 0 plus 0. And you can see that that's going to be 0 plus 0, which is 0. So in this case, we're asked to maximize. So we're comparing the numbers 12, 14, 10, and 0. 14 is the largest of those numbers. So that is going to be the maximum of this system of equations. It happens at the point 2.59. So you can say the maximum occurs at p equals 14 when x is 2.5 and y is 9. We could have done this same problem, and instead of saying maximize, it could have asked us to minimize. So if it asked us to minimize instead, we would do the same exact process. Everything is exactly the same. But in that case, we're now looking for the smallest value when we plug in our endpoints or our corner points. So the smallest value, whoops, I erased instead of highlighted. Let me try that again. So that's 0. The smallest value is 0. So we could say the minimum occurs at p equals 0 when x is 0 and y is 0. So depending on what it asks you to do will depend on your answer, right? If it asks you to maximize, you're going to be looking for the largest value you get when plugging in your corner points. If it asks you to minimize, you're going to be looking for the smallest value you get when plugging in your corner points.